Properties of alkanes. Well, alkanes have particular properties, such as because they are nonpolar, they have very weak intermolecular forces. These are all purely London dispersion forces that keep them together in, say, a liquid. So since these forces are so very weak, the melting points tend to be quite low. But wait a second. As they get longer and longer, the melting point is getting higher and higher. Why is this the case? Well, think about a bunch of pencils or other writing implements. So a bunch of long strings, basically. When they are all tangled together, it is hard to get them to start moving past one another. Tangled together in a nice big pile. So that would be like going from solid to liquid. It takes more energy the longer these tangled strings or ropes or whatever you want to think of them as are. Now for boiling point, similarly, if they're longer, it's harder for them to escape into the atmosphere, which means that the vapor pressure is lower. The point at which the vapor pressure is equal to 1 atmosphere, i.e. the boiling point at 1 atmosphere pressure, is going to be higher. Now, what are the units that we use in chemistry for temperatures? Well, we can tell that these are not kelvins. Why? Because there is no such thing as negative however many kelvins. So these are degrees Celsius, often written as just Celsius. But technically speaking, we should put a degrees symbol. Most teachers will let you get away with just Celsius instead of degrees Celsius. But hey. Now for isomers, you can see that initially there are no isomers other than the standard one. And very quickly the number of isomers grows absolutely huge. Now isomers will vary from the original, the long chain, in physical and chemical characteristics. For example, pentane, when you have pentane as being just one carbon linked to 4 other carbons, and so that's basically one ball, it does not tangle together very much with other pentane molecules. So this isomer it doesn't tangle much, it doesn't bond very much either intermolecularly, so it has a very low melting and boiling point compared to normal N-pentane, i.e. straight pentane. Now the longer they stretch, so the longer the main chain is, the higher melting point and boiling point will be. Now these characteristics allow what we call fractional distillation, which means that you have basically a distillation column. A lab distillation column is a bit more complicated, but the point is that it's cooler at the top and hotter at the bottom, and whatever manages to boil off, it will hit something, it will condense, and it will fall back down, but the bit that reboils while it's attached to whatever surface will have a higher proportion of the more volatile component than the original boiling initially gave you. So the concentration of the gaseous parts increases as you go up, and the concentration of the longer chains increases as you go down this column. Initially you start with crude oil, which must be heated in a furnace before it can be put in this distillation column, because, well, here we say fuel oil. Fuel oil used on ships is in fact heavy enough and thick enough that it must be heated before it can be pumped. Fuel oil was chosen mostly for the fact that it was very cheap, because it wasn't used for, say, tar, for asphalt, or lubricating oils, or for waxes. It wasn't long enough for that. It was also very hard to pump, so nobody else had figured out how to use it as fuel for, say, cars, because you don't have the weight and space on a car to fit a fuel heating system. So fuel oil was chosen for ships, and they designed engines for this for that reason. It is also remarkably inflammable. Actually, the term is non-flammable because inflame can be used to burn something. So fuel oil is actually relatively stable at room temperature, and yes, it'll burn, but it will not burn as vigorously or as explosively as gasoline or even diesel. So here we see a distillation tower at an oil refinery. We see a number of pipes coming out the sides at various intervals. These are used to extract various different grades of fuel. Now, reactions of alkanes. You might be surprised when you hear that alkanes are actually considered not very reactive. Why? Well, okay, we add acid, nothing happens. We add base, nothing happens. Well, what else can we do? Well, okay, we could try to add a strong oxidizer, such as oxygen gas or hydrogen peroxide. Nothing happens at room temperature. But when we heat it up enough and we add a little bit of energy to overcome the activation energy, i.e. a spark plug or just a spark in general, or a flame, then they are all combustible. And we note that sometimes you have to heat them to vaporization or close to vaporization before this combustion can really get going. Otherwise, they actually do not burn very fast. As you know well from, well, if you've ever lit a candle, those waxes are hydrocarbons. Wait a second. Why is it that I light a candle, there's a pool of melted wax under the flame, but the flame is not traveling down the wick and lighting that pool of melted wax on fire? I mean, this is pretty obvious to anybody who has ever lit a candle for a little while. The melted wax does not catch on fire in its liquid form. It has to be drawn up the wick, vaporized by the heat, and then it combusts with oxygen. This is very helpful because it would be very awkward if the front wheel of one's bicycle while we're riding it catches fire because of some random spark. Now, the bicycles have ball bearings and lubricating oil that make it so that you can actually turn it without much, well, excess friction. In other words, so that the bicycles are actually controllable. It would be very awkward without the use of these oils as lubricants. Now, they're also used as structural materials, such as plastics. And did you know that plastics, as used in composite armor, can actually be glass reinforced? For example, the upper front plate of the T-64, which was pretty much the first main battle tank to use composite armor, had a layer of glass reinforced plastic. That might sound extremely awkward, given that we all know that when you hit glass, it shatters. Mostly. But the whole point of that material was to shatter upon the enemy round's impact, and thus eat up some of its energy and spread its energy out into the plastic, which is a relatively soft material. And this is the same principle really as face-hardened armor. Face-hardened armor has the outer side treated so that it is impact resistant compared to the inside. When the outer side is hit hard enough to be pierced, it will crack and so on. This bleeds off some of the shell's energy. And the internal part is soft and yielding enough that it will absorb most of the impact. Hopefully. Of course, often this doesn't quite work because the shell is just too big or too fast. Now, complete combustion is what happens when, well, you have enough oxygen. So, you completely combust. Okay, that's pretty obvious. Complete combustion, you completely combust something. That is not how you should explain things. how you should explain things is actually more along the lines of it goes to carbon dioxide, water, and thermal energy. There is no soot, so no uncombusted carbon. There is no carbon monoxide, i.e. not completely oxidized carbon. Now, carbon chains fall in a few categories of length and characteristics. So these categories are 1 to 4. What is 1 to 4? Well, natural gas. Natural gas is what we typically call this category because, well, methane through butane are gases at room temperature, and thus they're used in, say, compressed gas cylinders as fuels, and in, say, gas heating of homes. Why is it more convenient to pump a gas than to pump a liquid through many pipes to supply homes? This should be quite obvious because gases flow easier than liquids. They have lower viscosity. It takes less effort at the pumping stations. Alright. 5 to 12. This is gasoline. And then 12 to 18 we have jet fuel. And 50 plus we know is tar. Well, what's in between then? Well, we know that diesel is anywhere from 8 to 12, 8 to 21 carbons. So we note that diesel fuel is in fact, well, jet fuel is a subset of diesel fuel, which is rather interesting given that early in aircraft development, they used petrol engines. And then they had the Jumo series of diesel engines for German bombers, for example. I believe the Junkers 88, or Junkers, depending on how you read it, used the Jumo engines. So those were diesel powered. And then it turns out that for jet engines, using gasoline is a little too volatile, because the working temperatures of jet engines are extremely high and the fuel lines around it are heated to rather high temperatures, and gasoline is a little too volatile. It will vaporize upon contact with those hot fuel lines and thus basically boil out as a vapor into the combustion chamber. Or when you're trying to throttle the fuel supply, you're going to end up having other issues such as too much pressure buildup in the pipes, and the pipes burst, which is bad inside a jet engine for what I hope are really obvious reasons. So jet fuel is actually a subset of diesel fuels. Now, bunker oil for ships is usually somewhere between the 20 and 40 range. So usually around 30 to 40s. And there are uses for these other fractions as well. For example, diesel can be used to heat homes. So stuff like home heating oil would fall in about this range. And then there is bunker fuel. Now, for ships, we should probably write down that it's for ships because I'm reasonably sure that not too many people know that bunker fuel refers to ships for fuel bunkers. Why are they called bunkers? Well, originally when ships burned coal, they were called coal bunkers. Why they chose the term bunker, given that, well, later on they called concrete fortifications bunkers, it's possible that it was because there are many possible historical reasons, such as early on when they were building protected cruisers, i.e. when they had steel ships. First of all, there was a big shift because steel is stronger than iron, and therefore even very light ships, comparatively speaking, could carry armor. They could carry both deck and side armor, which by definition made them armored cruisers, but that made later on for light armored cruisers, which evolved into light cruisers. But the point is that originally protected cruisers relied on a sloped armored deck. So the main deck is up here somewhere. So lines may vary, but it relied on a sloped armored deck to protect the main machinery spaces. And it had coal bunkers that were around here. These coal bunkers, in addition to the deck, were supposed to protect the internal spaces, i.e. the engines of the ship. So it is possible that these coal bunkers are called bunkers, and thus later protective buildings were called bunkers because of this reason. All right, so what about up here? Well, you have lubricant oils. We know that lubricants have to be, well, first of all, they have to be able to move around with relative ease. And we know that the shorter the chain, the easier these particles can flow past each other, these molecules. Which means that if bunker fuel has to be heated up before it can be pumped, that means obviously lubricants have to be rather lighter, rather shorter, and thus easier to move. Having lubricants that freeze into solids is very much not good, for what I hope are really obvious reasons. Now down here, 40 to 50, we have, well, instead of heating up to actually move it, instead of just being sludge, we have waxes. Now, tar and waxes may be 50 plus, depending on the properties that you particularly want. Now, waxes and what else? Petroleum jelly also falls into this category. There is a popular brand of petroleum jelly that I'm sure everybody is familiar with. In fact, petroleum jelly in Chinese, actually goes straight by the transliteration of that brand name, but due to brand name issues, we will not mention it. I am sure you can find out on your own if you're really interested in petroleum jelly. Now, an alkyl halide is an alkane in which one or more hydrogens have been substituted by one or more halogen atoms. So, if we were to draw this, we notice that these substituent groups are organized by alphabetical order. This is an important part of the naming of alkanes, or organic compounds in general. So, why is it, say if it was tribromo instead. If it was tribromo, this would still be in front of ethyl, because the base form is bromo, which is B, which is in front of E on the alphabet. So 1,2-dibromo-3-ethylhexane, we know that the main chain is 6, so 1, 2, 3, 4, 5, 6. 3-ethyl. 3-ethyl. 1,2-dibromo. Why is it that we chose this as the main chain instead of this? Well, it's because there are more substituents along this main chain than along that option. And because there are more substituents, when we name them, it's more convenient. Why? Well, otherwise you would have to be writing, 1,2-dibromoethyl, all in brackets. Well, let's do this. This is a little bit more awkward than this. Because, well, admittedly, it seems like the number of characters is the same. No, because you had more brackets. And it gets really complicated once it gets really much longer, or with many more substituent groups. Or complex substituent groups, such as, well, 4,1-chloroethyl-6-methylnonane. So nonane is 1, 2, 3, 4, 5, 6, 7, 8, 9, nonane. And 4,1-chloroethyl. Let's start at this end. Now, when you number on a substituent, you number 1 being the closest carbon to the main chain, to the point at which it attaches. So, this is 1-chloroethyl, and this is not treated as the main chain because it's shorter. And 6-methyl. That's a little bit cramped for space. So, in order to avoid confusion, I actually write out that this is CH3. Of course, when you're just starting out, it is strongly recommended that you draw out diagrams much bigger than this. This is a fairly compact form. When you just get started, writing bigger diagrams will prevent interesting mistakes, shall we say. All right, in summary, hydrocarbons contain hydrogen, hydrocarbon, so carbon. So they contain hydrogen and carbon, and only hydrogen and carbon. This is very important. So sugars, for example, which have oxygen, are not hydrocarbons. Amino acids have oxygen and nitrogen. They are not hydrocarbons. So in a saturated hydrocarbon, the atoms of carbon are bonded to each other by single bonds, and all the rest of the bond spaces are taken up by hydrogen. Suppose we had a mass of graphite, or just any chaotic form of carbon, or even diamond. If we have the outside be all attached to hydrogen atoms on the outside, then that chunk of diamond, with hydrogen coating the outside, would be a hydrocarbon, or one big hydrocarbon molecule. Now, or several, depending on the actual internal structures of that particular diamond. Because diamonds, while they are usually very good, they are not necessarily perfect in their tetrahedral arrangement of carbon atoms. Structural isomers are compounds with the same chemical formula, but different molecular geometry. So propane and cyclopropane are not structural isomers because, well, propane loses 2 hydrogens if it wants to cyclize to make cyclopropane. Alkanes may have a straight chain structure or a ring structure. So stuff like cyclopropane, cycloheptane, cyclohexane, cyclopentane, cyclobutane, or cyclodecane, or desane, well, these are all cyclic. So cyclo is the beginning that we use for cyclic. So, what about dimethyl cyclopropane? Well, dimethyl cyclopropane, you're probably thinking, hey, where are the positions? If this was butane, cyclobutane, we would need positions. But for cyclopropane, there are no positions involved until you consider the fact that because this is locked in a ring, these atoms can't freely rotate around each other. So the particular orientation, well, this could be above the ring, and this one could be also above the ring. So they could be on the same side, or they could be on opposite sides. If there was one that was below the ring, it would be drawn like this. So that is a complexity that we will not do yet. We will do that later. Stereochemistry for now is beyond the scope of our current section. We will do it a little later. So, you probably have heard of stereocenters and stereoisomers, though, at some point if you took biology class. Yes, okay, it is important, but later. Now, substituent groups may be attached to the parent structure, or there may be no substituents, such as just cyclopropane or cyclobutane or whatever. We note that there are many colloquial names that are actually sometimes mostly accepted by IUPAC. For example, isopropyl alcohol. I mean, yes, that is a colloquial name. Ammonia is a colloquial name as well. But IUPAC is fine with these. Why? Because they are so old that they're just grandfathered in. Water, that's a colloquial name. Water is a very colloquial name. So, why is it so in there? It's too old. Everybody's used to it. Now, alkyl halides are alkanes in which halogen atoms have substituted for one or more hydrogen atoms. Now, when we write out the names, we go in alphabetical order of the base groups. So something like bromo, chloro, so on. And we note that if we have, say, an ethyl group and then an iodo group, then we put the ethyl first with the number for it ahead of it. So say 2-ethyl, although you will very rarely see something like 2-ethyl. Why? Because this would make a longer chain, and thus this is usually going to be, if it's just for convenience, fine. Yeah, sometimes this happens. But, well, 2-ethyl is really not something you'll see unless you are doing something like 2-ethylbutyl. Now, this is a valid side chain. This might be on, say it's on position 5. Now, if it's on position 5, then why wasn't the other chain considered the side chain instead if it's just a straight chain? Because, well, 5, you have 4 here. So that's 4 carbons. This could have been the main chain, except we would make there be, say, something like 1, 2, 3, trichloro. Now, we note that B here, the main chain of this substituent group, and the C here are what we use to consider the alphabet. Trichlorodecane, or something similar. So you could end up with something like this. Be careful when you're naming side groups that have substituents. When in doubt, feel free to use brackets and such to denote them properly. Alright, that's actually it for this section. And we'll see each other again next section when we talk about some hydrocarbons very closely related to alkanes. Now, if alkanes have all their carbons single bonded to one another, what do you think the logical next step for us to learn is?